Okay. All right. So we're going to go ahead and get started. So this is the test number 2, which covers chapter 3. This is for the full semester class, not the 8-week semester. And this is for the online elementary statistics. So we have, let me look how many questions. We've got 28 questions to get through today. And so we're just going to go ahead and jump on in. My name's Maxine. I work in the Academic Support Center. I'll be emailing the recording out to everybody that's ever given me their email address for this class. So you can have a copy of the recording. I know for a lot of people, it's not feasible to attend the sessions live. And then in that email, I'll have like my hours, how you can get help at other locations and from other people and stuff like that. But okay, let's jump in. So get my calculator here. All right, use the fundamental counting principle to solve the problem. I'm going to zoom in just a little. Can do that on these. Okay. Turn the light on. There we go. How many different codes of 4 digits are possible if the first digit must be 3, 4, or 5, and if the code may not end in a 0? Okay, so when it's talking about the fundamental counting principle, what we're going to be doing is we're going to essentially create some blank spaces for each of the digits, and we're going to fill each of these spaces in with the number of options we have for each of them, and then we're going to multiply those things together. Okay, so this is a 4-digit code. So this is the first digit, this is the second digit, this is the third digit, and this is the fourth digit. And the lead for my pencil is going to break a lot today. I'm just going to ignore it and just move on with life when it happens. Okay, so let's talk about some of the restrictions that we have here. So we have that if the first digit must be a 3, a 4, or a 5. So that's 3 different numbers that it can be, 3, 4, or 5. So we only have 3 options for that first digit. Right, so for the first digit, it has to be those 3 specific numbers, one of those 3 specific numbers, so we have 3 options for the first digit. Then the other restriction that we had was that it's not allowed to end in 0. So a quick note here is that the options that we have for digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, which all together is 10 digits. Okay, so we have 10 digits available to us, except the last digit can't be 0. So instead of having 10 digits, one of those options is gone. Now we only have 9 digits available. So we only have 9 options for our 4th term. It did not give us any sort of restriction about the 2 terms in the middle. So we can use any of these 10 digits for the second, and we can use any of these 10 digits for the third number. So what we're going to do is we're just going to take those, that's for a different class, and we're just going to multiply them together. Now you can do this in your head if you want to get that 2,700 or 2,700. Like if you wanted to say 3 times 9 is 27 and then add 2 zeros because we're multiplying by 10 2 times, you can do that. Or you can just be extra safe and just plug it in the calculator to be super sure that you have the right answer. So yeah, there's a variety of different ways to solve many of the questions in this chapter, but you guys are going to find which ways make the most sense for you and which are easiest for you and which take the least amount of time. But if they say using the fundamental counting principle, that's where we're creating these sort of blanks and we're filling them in with the number of options that we have for each of those terms or for each of those digits or letters or whatever they are, and then multiplying all of them together. Okay. All right. Okay, so use, again, the fundamental counting principle to solve the problem. A singer-songwriter wishes to compose a melody. Each note in the melody must be one of the 12 notes in her vocal range. How many different sequences of 3 notes are possible? So we're saying we have the first note, the second note, and the third note. Short little melody. And each note can be any of the 12 notes in her vocal range. So we have 12 options for that first note. And we're allowed to use all 12 again for the second, and we're allowed to use all 12 again for the third. The melody can be the same note 3 times in a row. That's fine, because they didn't give us any restrictions on what can be used for the first, second, or the third note. So there's a couple different ways to plug this into the calculator. We can literally just do 12 times 12 times 12, right? Or we could say 12, and then we could use this button right here, this little caret symbol, to say to the power of 3, because 12 is being multiplied by itself a total of 3 times. So that means it's being cubed. So that's another way that you can plug that into the calculator. All right. Okay, some of these are fast. Okay, if an individual is selected at random, what is the probability that he or she has a birthday in July, and ignore leap years? Okay, so we're talking about probability. So they want us to focus on if they have a birthday in July. So for a lot of probability, you can kind of think of it as like fractions, like the part over the whole. The part is the number of days in July, is specifically what we're looking for. And it's out of our entire sort of sample space, or the whole thing, or in this case, the whole year. So the number of days in the year, right? So the part over the whole. So they're expecting you guys to know how many days are in each month. Honestly, I have to sing the little ditty that I was taught when I was a kid to remember it. I can't remember it otherwise. So the whole, 30 days has September, April, June, and November. All the rest have 31, except for February. And in leap years, which has 29, and in leap years 28, or however that goes. I might not be remembering it right. But all that to say that they expect that you guys will know how many days are in July, and they're saying ignore leap years. So if it's not a leap year, there's 365 days in a year. So that's how they're getting 31 over 365. Now, another note that I want to make is that maybe you didn't look at your options before you started working this problem out. And so maybe, you put the 31 over the 365, and then you said, okay, let me plug that into the calculator, right? 31 over 365. And then you get this decimal, and then you go to look at your answers and realize, oh, I didn't need to plug that into the calculator. They just wanted me to leave it as a fraction. So a good test taking strategy or tip is to take a look at what the answers look like before you start solving the problem, so that you don't do any extra work. Like, you don't want to do any more work than you absolutely have to, right? Finn, hello, welcome. Just wanted to give you a heads up that we are recording this. I'll be sending the recording to everybody afterwards, but I am required to let people know that we are recording. So we've got how many questions again? I think 28. Yeah, 28 questions that we're going to be going through today for the review. All right. Okay, so the distribution of blood types for 100 Americans is listed in the table. If one donor is selected at random, find the probability of selecting a person with blood type A positive or A negative. Okay, so when you see that word, or, there it is. I was like, where's the word or? That tells you that you're going to be using the addition rule. Okay. All right, so the addition rule says that the probability of A or B, and by the way, when I say A or B, I'm not talking about blood types here. I'm talking about a particular event A and a particular event B. Actually, you know what? Just for ease of understanding here, I'm going to use different letters, just because this problem has A's and B's already. I don't want to confuse things. Normally, when we write this rule out, we use A's and B's. Okay, so the probability of event X or event Y is the probability of event X plus the probability of event Y, and then you subtract the probability of where those two events overlap, the probability of X and Y. So sometimes when you're solving problems where you're looking for an or, probability of this or that, sometimes you're going to have to use this whole equation. But sometimes this is not a thing that actually occurs. Like sometimes X and Y don't overlap. There is no overlapping of the two things. And so you end up just adding the two together. So again, if you see that word or, that tells you you're going to use the addition rule. And this is the addition rule. Add them up, subtract where they overlap. And the reason that you have to subtract where they overlap, just to kind of give you guys some context here, like if I called this circle is X, this circle is Y, and I wanted the probability of X or Y. If I colored it, let me get my colored pens here. If I color in X, right, so I'm going to take all of X, okay, and then I'm going to color in all of Y. Well, I just counted that space in the middle twice, right? I counted that middle space once for X and then once again for Y. So this space in the middle got counted twice. Well, I'm not supposed to count it twice. So that's why I have to subtract one instance of where it overlaps. So that's why this rule exists the way it does. So hopefully that'll maybe help you guys remember what the rule is. But all right, so let's apply that rule to our specific situation, okay? We're going to do the probability of A positive blood, right, type A positive, plus the probability of A negative blood. We're going to add those two together, and then we're going to subtract the probability that somebody has A positive and A negative blood. Well, if we look at this, everybody's blood type is only one, right? Nobody has a blood type that is both A positive and A negative. It's one or the other. So this isn't something that exists. Or if you did want to plug something in for it, you could say it's 0, right? 0 is the probability that somebody has blood type both A positive and A negative. But let's focus on finding these. So the probability that somebody has A positive blood, well, if we look at A positive, there's 34 people. So we were talking about the part over the whole, right? Part over the whole. The whole is the 100 Americans that were listed in this table, right? So out of the 100, and I'm going to go ahead and set that up for both of these. They both have a denominator of 100. So out of the 100 Americans that were surveyed here, how many of them had A positive blood? 34 of them did. Okay, and now we need so the probability of A positive blood is 34 out of 100. Or we could write that as the decimal 0.34. You don't have to have the 0 there, but it's just 0.34. For the probability of A negative, same thing. We're just going to look and see, well, what's the number that it has there? It has a 6. So if I wanted to write that as a decimal, it would be 0.06. So you don't have to turn these into decimals right away. If you wanted to, you could just keep them as fractions. They already have a common denominator. So the rule is when adding and subtracting fractions, you keep your denominator and you add or subtract across the top. So 34 plus 6 is going to give me 40. And if I take that and plug it into the calculator, I get 0.4. You could also, if you didn't feel comfortable adding the fractions together, you could do the fractions in the calculator. I would just suggest when you're dealing with fractions, use parentheses, right? The little parentheses here. So 34 out of 100 plus 6 out of 100, and you get 0.4. Okay. So however you break it down, you should be getting 0.4. Or, if you want to write 0.40, that's fine. Just I don't want you to get thrown off if you write 0.40 because you're saying, oh, 34 and 6 is 40, or 34 and 6 is 40. That's the same as 0.4, right? Because there's technically an infinite number of zeros after that. We just don't write them all. Okay. All right. Okay, the distribution of master's degrees conferred by a university is listed in the table. We've got a variety of degrees and their corresponding frequencies. What is the probability that a randomly selected student graduating with a master's degree has a major of engineering? Round your answer to 3 decimal places. So we've been talking about the part over the whole, right? But we don't know the whole here. They didn't just come out and give us that number, but that's okay. We can find it, right? Just like we did back in the previous chapter, we can say, well, what is the sum of the frequencies, right? That's sigma, capital sigma. We're going to add all of these up together, right? So we're going to say 216, 27, 16, x plus 222. Okay, so we have a total of 888 master's degrees that were conferred by this university. So that's going to be our denominator. Okay, and our numerator is going to be the specific thing we're looking for, the number of people who have who got their master's in engineering. So that's this number right here, 67. And I see, well, not only do I see that we've got decimals here, but also they specified round your answer to 3 decimal places. So we're going to take this 67 over 888, plug it into the calculator, and we're going to round this to 3 decimals. So I always, at every single review, I take a minute to do a quick refresher on rounding rules because a lot of people forget rounding rules, and I never want you to get a question wrong because you rounded wrong when you did everything else right. Okay, so they told us to round to 3 decimal places. So I go 1, 2, 3. This is the place they want me to round to, so I'm going to underline the place that they want me to round to. I'm going to look to the number to the right. If the number to the right is 5 or more, then the underlined number goes up 1. But if the number to the right is not 5 or more, the underlined number stays the same. So this is not 5 or more, so this is going to stay the same. So it's going to stay 0.075, which is how they got that. Okay. You don't want to like round twice because then you'll get the wrong answer, right? Like if I accidentally rounded to here first and then said, oh, now I have to round and round to, you just don't do that. You round the one time to the decimal they tell you to. Okay. All right. All right, explain why the statement is incorrect. The probability of rain tomorrow is 136%. So when we're talking about probabilities, the probability of some event A, is always going to be between 0 and 1 inclusive. And what I mean by that is inclusive meaning it can be 0 and it can be 1. If a probability is 1, that means that it is certain. The probability that I'm going to wake up today is 1. I did wake up. It already happened. I'm certain of it because I'm here and I'm talking, so I must be awake. So the probability of that is 1. That's as high as you can go. You can't be any more than that. You know how people talk about like, oh, you need to give it 110%. Yeah, you can't do that in probability. You can only be 100% certain. You can't be 101% certain of anything. Okay. And then down here at 0 is things that will never happen or things that are impossible. Okay, so like if I were to say, like if I look out the window and I see that it's raining and I say the probability that it's not going to rain today would be 0 because it's already raining. It's impossible for it to not happen because it's already happening. Okay, now 0 is different than 0.00000001. You might have a super tiny number, but that's not the same as it being 0, like being completely impossible, right? Like the probability of me winning the lottery. I mean, I haven't bought a ticket, so it's going to be 0. But if I did buy a ticket, it's a really small number, but it's not 0, right? So just be aware of that. Point is, between 0 and 1, we can be 0 and we can be 1, but we can't go beyond that, right? I can't be any higher than 1 and I can't be any lower than 0. So the probability of rain tomorrow is 136%. No, that's not possible because it's over 1. Also, this is 100%. This is 0%, right? These are the decimal versions. These are the percent versions. So choosing these, the probability of an event cannot exceed 100. Okay. Take a quick water break. My throat's a little dry, so this is a reminder, stand up, stretch, get a drink of water. You want to stay hydrated. I know we could all drink more water than we are. Okay. All right, so the probability that an event will happen is probability of the event is equal to 0.44, right? So we say that's how we read this, is probability of event E is 0.44. Find the probability that the event will not happen. So this is the probability that it will happen. They want the probability that it won't happen. So what we're finding is what's called the complement. Complement, okay? So I think they do talk to you guys about the notation in that. And it's the, yeah, I think they do the little apostrophe, probability of E, probability of the complement of E. But both of those things added together is going to be 1. So either it's happening or it's not happening, but both of those together are 1. So like for instance, if they said that the probability of something happening was 85%, then the probability of it not happening is whatever I would have to add to this to get to 1, right? So that would be 15%. And that's how I would get a probability of 1 or 100%. Sorry, I'm just trying to get some more lead to poke out of my pencil. All right, let me switch over to my other pencil. Okay, so that's how we get 1. All right, so in our case, we have that the probability of event E is 0.44 plus, and we're saying plus something is going to give us 1. That's not a 0, that's me circling that, saying something, right? So this is the probability of not E. So a kind of fast way to do this, instead of kind of reasoning your way through it each time, is to just subtract it from 1, right? Just say 1 minus the probability of E is going to give me the probability of not E, right? So 1 minus 0.44 is going to give me the complement of that. So 1 minus 0.44 is going to give me 0.56. Right? And we can always use your calculator if you're not 100% sure of doing it, excuse me, doing the math in your head, right? So it is good to try some of these in your head. You want to keep your mental math skills sharp by practicing them. But when it comes to the test, anything that you do in your head, plug it into the calculator just to be sure that you're getting it right. Just like I don't want you to get a question wrong because you rounded wrong, I don't want you to get a question wrong, especially on these fill in the blank ones, because you did some mental math incorrectly. Okay? All right. Okay, the frequency distribution to the right shows the number of voters in millions according to age. Consider the event below. Can it be considered unusual? A voter chosen at random is between 35 and 44 years old. So let's take a look at what we have here. 35 to 44 years old, and we have a frequency of 26.9. So that's just a frequency. That's not a probability, right? So we're going to have to first calculate what is the probability before we can determine if that probability is unusual or not. Okay, so we're going to, just like we did before, we're going to say, well, what's the sum of the frequencies? So we're going to add all of these together, right? Oh, hold on, 24.6, yeah, 26.9. Nope. Okay, so we get 148.4. Okay, so we're going to do the, that's the whole, right? That's the total is 148.4 million. Okay, so that's our denominator. And our numerator is the frequency of this particular thing that we're looking at, which is the 26.9. So if we plug this into the calculator, and real quick, in case you didn't know, because I want to divide by this last answer that I had, but I don't want to type in that number, or maybe it's a bunch of digits and I don't want to type all of them in. Down here at the bottom where it says ANS above the negative sign, that's answer. I want to use the answer from the last calculation. So to get that, you see how it's above the button? We're going to use second. It's kind of like a shift. So I'm going to go second answer. And so I'm doing 26.9 divided by the last answer I had. So that's going to give me about 0.181. Okay, so we have our probability there. That's the probability that a voter chosen at random is between 35 and 44 years old. So now we have to look at it in relation to what is considered unusual. Okay, so they're using kind of broad terms in this question, but they get a little bit more specific later on. Okay, so you can see some of these options here. They're talking about being close to 0 or close to 1, not close enough, too close, blah, blah, blah. If you have, so we talked before about like we've got 100%, or I'm sorry, we've got 0% and we've got 100%. Okay, and if the probability of something is less than, and this is not going to be to scale, but if it is less than or equal to 5%, that's considered unusual. Okay, so if the probability of some event is less than or equal to 5%, that's considered unusual. Okay, well, this is not less than 5%. This is 18% approximately, right? So this is about 18%. So maybe that's closer to here. That's not unusual. I mean, it's kind of low, but it's not unusual. So we would say, no, the probability of the event is not close to 0. It's not close enough to 0. It would need to be 5% or less in order to be considered unusual. Okay. Okay, classify the events as dependent or independent. So event A is a red candy is selected from a package with 30 colored candies and it's eaten. Event B is a blue candy is selected from the same package and eaten. Okay, so we're going to go through the like actual technical rule, and we're also going to go through how you can sort of reason through it, okay, about whether the events are independent or dependent. So in order to illustrate this, I'm going to assign some numbers. It's going to be easier to deal with actual numbers. So I'm going to say, so they're saying that there's 30 candies in this bowl or bag, package. There we go, package. So it's 30 candies in the package. I'm going to say that 20 of them are red and that 10 of them are blue. Okay, so that means, so we have 30 candies. Candies. Oh my gosh, I can spell, I promise. And we're saying that 20 of them are red and 10 of them are blue. Okay. So the actual real definition, when we're talking about two events, event A and event B, is that, I guess let me write it over here. If the probability of B is equal to the probability of B given A, which we'll talk about that in just a second here, then the events are independent. So again, the way that we read this is the probability of B given A. That's what that vertical line is. We say given. Okay. And if the probability of B is not equal to the probability of B given A, then the two events are dependent, right? So that's the kind of like actual definition. So let's talk about what those things are individually. So the probability of B, just B, all on its own, forget about A, just the probability of B. Let's find that. So event A, we're going to ignore that. Event B, a blue candy is selected from the package, right? We're only talking about B. Okay, a blue candy is selected from the package. So we want the probability of that. So it's going to be the part over the whole. The whole is 30 candies. The part is the 10 blue ones, right? So that's giving us a probability of 1/3 or 0.3333. It's 0.3 repeating, but it's 1/3, okay? So that's the probability of just event B, not talking about A. So now let's talk about what is the probability of B given A, right? So we're going to start with event A having happened, and then we'll calculate if after event A happens, then B happens. Okay, so I've got a package. I'm going to call it a bowl. I've poured them into a bowl. I've got a bowl of 30 pieces of candy. I'm going to fish out a red piece, and I'm going to eat it. My denominator is no longer 30. I don't have 30 candies anymore. When I go to pull a blue candy, I don't have 30 candies to choose from. I now only have 29 candies to choose from. Okay, out of the 29 candies, how many of them are blue? Well, I still have 10, right? I didn't pull a blue candy. I still have 10 blues. So my numerator didn't change, but my denominator did change. I have a different denominator now. So when I go to divide this, I'm getting a different number, right? And I'm just rounding here. So the probability of B given that A happens is not the same as just the probability of B completely on its own. So the probability of B is not the same as the probability of B given A in this instance, which means that these two events are dependent, right? And you can kind of think of it in the way that we normally think about these words, right? Dependent versus independent. Event B, the probability of this depends on whether or not A happened. If A happens, it changes the probability of event B. That's what this boils down to, is does one thing happening affect the probability of the other one? And in this case, yes, it does. Okay. All right. Okay, a group of students were asked if they carry a credit card. The responses are listed in the table, and you can see that either you're a credit card carrier, which is this column, or you're not a credit card carrier, that's this column. And then they were broken down into either freshmen or sophomores. And then they've given us the totals, which is nice. So it says if a student is selected at random, find the probability that he or she owns a credit card given that the student is a sophomore. Round your answer to 3 decimal places. Okay, that word given is defining your sample space. So literally, if you see that given, whatever the given is, becomes your sample space. So it's like you've put on blinders and you're only allowed to look at what is given. So what is it that was given? Given that the student's a sophomore. So what we're saying is that we can only look at this row right here. So our whole world just got shifted and we can only look, I can't really cover that up. We can only look here. That's the only thing we're allowed to look at. That is our new sample space. That is our new denominator. All the sophomores, the total sophomores is 40, right? So let's write this out in words, actually. The total number of sophomores. That becomes my denominator because that's my given, so that's my sample space. Okay, and then what specifically are they asking for? That they own a credit card. So the numerator is going to be that specific part. It's the number of credit card carrying sophomores. Right? So they're talking about that somebody owns a credit card. That's this column right here. But remember, we're only allowed to look at what was the given. We're only allowed to look here. So this number right here is the only number we're allowed to look at from this owns a credit card column, right? So your given is the number in the denominator, and where that overlaps with what they're asking for is the thing that goes in the numerator. Okay, so again, the given, the total for the given is what goes in your denominator, and where it overlaps with the thing they're specifically asking about is what goes in the numerator. Okay, and then we would take that and we would plug it into the calculator, 34 out of 40, and that's how they're getting 0.85. And also you'll notice here that it says round your answer to 3 decimal places. If your answer stops at 2, you can always stick a 0 at the end, right? There's an infinite number of zeros after that 8.5. We just choose not to write them, but they want 3 decimals, so we're going to put one more 0 there to make it 3 decimals. Oh. Have some more water with me. All right. Okay, so what is the difference between independent and dependent events? So we kind of already talked about this in that other problem, but you can see the way that they're wording it here. They're saying 2 events are independent when the occurrence of one event does not affect the probability of the occurrence of the other event. And we're going to do some problems that have that so that you can see that kind of in action. But 2 events are dependent, like the one that we did earlier, when the occurrence of one event affects the probability of the occurrence of the other event. So the probability of, pulling a blue after first pulling and eating the red, that affected it. That was dependent. Okay. Okay. So the accompanying table shows the results of a survey in which 250 male, 250 female workers aged 25 to 64 were asked if they contribute to a retirement savings plan at work. Complete parts A and B below. Okay, so find the probability that a randomly selected worker contributes to a retirement savings plan at work, given that the worker is male. So we're going to use this for A and we're going to use this for B. I copied and pasted the little table twice so that we could mark up all over it. Okay, so given that the worker is male, you know what? I'm going to use my highlighters instead of my pens here. Let me get some highlighters out. So what did we say about given? Given becomes my denominator. So they want given that the worker is male. So we're going to go and we're going to highlight this row. And sometimes the thing that you're given is a column, and sometimes the thing that you're given is a row. I just said that backwards. this is a row, this is a column, sorry. So yeah, so sometimes what they give you is this way, sometimes what they give you is this way. It can be either one, doesn't make a difference. All right, so that's our given. So our given is the total number of males. So in this case, we had 250. Okay, and once we've established that we're only looking at the males, they want to know the probability that they contribute to the retirement savings plan. So that's this column right here. But remember, we can only use what we've highlighted in pink or whatever color you happen to choose. So where the given overlaps with the specific thing they're looking for, that's what goes in your numerator. Excuse me. So we're going to plug that in, 118 over 250, and that's how they're getting that 0.472. Okay. All right, now for part B, it says find the probability that a randomly selected worker is female, given that they contribute to a retirement savings plan at work. So the given is that they contribute. That's the given. So the total for the given is 268. And out of that new sample space of just those 268 people, what's the probability that of those 268 people, somebody is a female? And again, I can only use the numbers that I've highlighted in pink. So I can only use where female overlaps with what is given, which is the 150. Okay, so again, we plug that in. Move this over a little. 150 out of 268. And if we take that and round to 3 decimal places, that's how we're getting 560. Let's actually do that rounding together, just so that if you guys run into this type of situation, you'll know how to handle it. 4925. Okay, so they want us to round to this. We look to the number to the right. If this number is 5 or more, it makes this go up 1. It is 5 or more, so this needs to go up 1. This is already a 9, so that's going to force this one to go up 1. Right? This is like saying 59 goes up to 60. Right? That's the only situation in which you're going to change any number that's to the left of the one that you've underlined, is if the thing you've underlined is a 9. That's the only situation that would cause you to change anything to the left of that. Okay. All right. Okay, so for the given pair of events, classify the two events as independent or dependent, flipping a fair coin and getting tails, and flipping the same coin again and getting heads. So you can see here, they're saying that they're independent because the occurrence of one does not affect the probability of the occurrence of the other. And I think sometimes people might get a little confused with ones like this because they might say, oh, well, it's, excuse me. I might say that, oh, it's supposed to be a probability of 50-50, right? 50% for tails and 50% for heads. So, oh, if I'm looking at, two being flipped, if one was tails, I should have a higher chance of getting heads, right? But here's the thing is the coin doesn't know that, right? The coin doesn't, have a brain and says, oh, well, I flipped tails last time, I better flip heads this time. It's not doing that. Okay, each flip is completely and totally independent. If you flip a coin 1,000,000 times, you're going to get really, really close to 50% heads and 50% tails. It's probably not going to be exactly, but it's going to be really, really close. But if you only flip a coin 6 times, you might not be getting 3 heads and 3 tails. The more that you do the experiment, the closer you're going to get to that theoretical probability of 50-50, right? The closer the practical or real probability is going to get to the theoretical. But it doesn't affect the next one that happens, right? So that's what they're trying to get you to understand here, is that just because you flipped a coin and got something specific, that doesn't change what happens the next time you flip that same coin. Okay. All right. Okay, so we're dealing with cards here, a deck of cards. So 2 cards are selected from a standard deck of 52 playing cards. The first card is not replaced before the second card is selected. Find the probability of selecting a jack and then selecting a 6. So a few things to note here. So they do expect you guys to know what a deck looks like and is made up of, and how many cards there are of each type, and um, and all of that. Okay. So this little diagram here was not provided in this question. I took a picture of this from the textbook and pasted it into here so that we could look at it as we were doing this. Now here they told you that there's 52 cards in the deck. They're not always going to tell you that. They're going to expect that you know that there are 52 cards in a deck, which is something that not everybody knows. So if you already know about how a deck is, like the components of a deck, great. You can ignore me for the next minute or so. But if you're not familiar with it, a deck is made up of 52 cards. There are 4 suits. Half of the deck or 2 of the suits are red. Half of the deck or 2 of the suits are black. Every suit is a color and a shape, right? So we have hearts, which are red. We have diamonds, which are red. We have spades, which are black. And we have clubs, which are black. Every suit has the same cards in terms of 2 through 10, Jack, Queen, King, and Ace. The face cards is something that we're going to run into. Those are kings, queens, and jacks, because they literally, if you look at a deck of cards, they will have a face on them. An ace is not considered a face card because there is no face on the ace card. Okay. All right, having said all that, let's take a look at what this problem is asking us to do. So they are asking for the probability of selecting a jack and then selecting a 6 if you're not replacing it. So what we're going to do here is the multiplication rule. These events are dependent, okay? So this is the probability of A and B. We do the probability of A times the probability of B, B given A. All right, so we're going to create 2 fractions and we're going to multiply them together. One fraction is going to be the probability of event A happening, which is this right here, which is selecting a jack. So let me write this down here. Probability of A is the probability of selecting a jack. Okay, and then the probability of B given A is the probability of selecting a 6 after pulling and not replacing, right? It's not replaced and not replacing a jack. Okay, that's what each of those things are. Okay, so the probability of A, the probability of selecting a jack. So keep talking about the part over the whole. The whole is how many cards do I have to choose from? Well, I have 52 cards to choose from at the very beginning before I do anything, right? How many of those are jacks? Well, I have a jack of every single suit. There's a jack of hearts, a jack of diamonds, a jack of spades, and a jack of clubs. So that's 4 hearts. No, not hearts, jacks. Sorry. So I have 4 cards that are jacks. Okay, so I'm going to select one of those. I'm going to remove it from the deck and not replace it. So now, when I look at selecting a 6 after not replacing a jack, I no longer have 52 cards to choose from because I pulled one of them out. I pulled a jack out. So instead of 52 to choose from, I only have 51 to choose from. And out of those 51 cards, how many sixes are there? Well, I have 4 6s, right? I didn't pull a 6 out. I still have all 4 of these 6s to choose from. So I still have 4 6s to choose from, but I only have 51 cards total. Okay. So this is the probability of A. This is the probability of B given A. And we're going to multiply these two things together in order to get the probability of both of them happening. Okay. So in the calculator, I always suggest if you're dealing with fractions, just be extra safe, use parentheses. Okay. And they wanted us to go to 3 decimal places. So when we go to 3 decimal places, we get 0.006. Okay. All right. Okay, a patient has a 59% chance of surviving bypass surgery after a heart attack. If the patient survives the surgery, then the patient has a 70% chance of making a full recovery. Find the probability that the patient survives the surgery but does not make a full recovery. Okay, all right. So again, we have the probability of A times the probability of B given that A occurred. Okay. So what these things represent is we're looking at the probability that they survive the surgery, okay, but then that they don't fully recover, right? Because you can survive a surgery but never kind of fully get back to like a full recovery. They don't fully recover. Okay. All right. So if the patient survives, or sorry, a patient has a 59% chance of surviving bypass surgery. Well, there we go. That's that right there. 59% chance of surviving bypass surgery after a heart attack. If they survive, then they have a 70% chance of making a full recovery. Okay, well, that's great, but that's not what we're trying to find. We're trying to find the probability that they don't fully recover. So we're going to have to find the complement, right? So we've talked about this before. The probability of making a full recovery plus its complement, so the probability of not making a full recovery, is equal to 1, right? So the probability of not is, if we were to like try and get this by itself, we could subtract this to the other side. I mean, you can look at it lots of different ways, but probability of yes making full recovery, right? We talked about this before, right? Just subtract it from 1 to get the other one, right? Don't feel like you have to make it complicated and write the formulas out. I'm just kind of showing you why you're allowed to do this math. The probability of making the full recovery, given that they survive the surgery, is 70%. So the probability of not making a full recovery after surviving the surgery is 30%, right? 1 minus 0.7 is 0.3. Okay, so that's the probability that they don't fully recover given that they survive the surgery. That's this right here. They don't fully recover given that they survive the surgery, because that's what that said, that if they survive, a 70% chance of making the full recovery. So now we can take these two things, plug them into the calculator. And that's how we get 0.177. Okay. All right. Decide if the events A and B are mutually exclusive or not mutually exclusive. And they're telling us that a person is selected at random. You guys may have heard this phrase before, just in your everyday life, things being mutually exclusive, it means they can't both occur, right? Mutually exclusive events cannot both occur. There is no overlap between them. They can't both be true at the same time. Okay. So somebody's birthday is in the fall and their birthday is in October. Well, there absolutely is overlap there. October is in the fall. Even if only part of October was in the fall, which it isn't, the whole thing is in the fall, but even if only part of it were in the fall, then there is overlap there. Those two things are not mutually exclusive because those two things do have overlap. Now, if somebody said that a birthday was in the spring and it was in October, then we would say, no, no, those things are mutually exclusive. October has no overlap with spring at all, right? So just make sure you understand the vocab word there. Mutually exclusive events, those are events that do not have any overlap. They cannot both occur. Okay, the table lists the smoking habits of a group of college students. If a student is chosen at random, find the probability of getting someone who is a man or a woman. Round your answer to 3 decimal places. Okay, so there's 2 ways to do this problem. I'm going to show you the longer way, and then I'm going to show you the shorter way. And when I show you the shorter way, if you don't already know what the answer is, you're going to say, oh man, I should have seen that. Okay, so we have this or, all right? So if you guys remember, when we see that or, that's the addition rule, right? And the addition rule says that we take the probability of the one thing, we add it to the probability of the other, and then we subtract the probability where they overlap. Okay. All right. So in this survey, let's take a look at how this survey was labeled. So people were given the option to state if they were a man or if they were a woman, and they were given the option to select if they were either a non-smoker, a regular smoker, or a heavy smoker. Those were the only options they were given. Okay. All right. So we're going to start with the probability that somebody is a man. So the part over the whole, we're going to take a look. The whole is all 421 people. And out of those 421, 203, and by the way, I'm getting 421 because it's down here, right? It's the total of all of the totals is 421. Okay, the probability that somebody is a man is, okay, there are 203 total people. I'm sorry, 203 total people who responded with man. Okay, so now we're going to find the probability that someone is a woman. Again, same kind of general idea where we have the denominator is how many people total there are. How many women we have specifically is what's going to go in the numerator, right? So the total number of women that we have is 218. Okay, and then we're going to subtract any overlap. Well, there was no overlap because there wasn't a third option that said, I am both a man and a woman. People were not given that option to fill in. So there's no overlap there. So we're not going to subtract 0. We had a problem earlier like that where there was no overlap between the two different categories. Okay, so we're going to add these two fractions together. So we keep our common denominators already there, right? Both have a denominator 421. So we're going to add up 203 plus 218, and we get 421. And if we take that and put it in the calculator and divide it, we get a big fat 1, right? So this was the long way. The short way is to say, they asked us to find the probability of getting someone who is either a man or who is a woman. Well, those are the only options that we were given, right? There is no third option or fourth option, right? So we've just covered the entire sample space. Everybody who answered had to say that they were either a man or a woman. So this problem could have been reworded and they could have said something like, find the probability that someone is either a non-smoker, a regular smoker, or a heavy smoker. And we would have the same answer. It would be 1, because those were the only 3 options that we were given. And if we want the probability of this or this or this, then we just gave everything. So it's the whole sample space. So in this case, it was the probability of this or the probability of this. So that's the whole sample space. So that's why it's 1. So if you see a problem like this on the test, they don't need you to take your time to do the calculation here to get 1. You can just say 1 if you notice that they're asking for the entire sample space. Okay. All right. Okay, the distribution of master's degrees conferred by a university is listed in the table. Assume that a student majors in only one subject. Okay, so no double majoring here. What's the probability that a randomly selected student with a master's degree majored in business, education, or engineering? And then round your answer to 3 decimals. So we have the probability that they majored in business plus the probability that they majored in education plus the probability that they majored in engineering. And then I'm not going to get into the whole what we would subtract here for 2 reasons. One, because they've told us specifically there is no overlap. Everybody is only majoring in one thing. There's no double majors or triple majors or anything like that. Everybody is only one subject. So there is no overlap. You're either this or you're this or you're this, but you're never 2 of those. The other reason that I'm not going to get into how to do that is because it's a little bit more involved than the subtraction that we've talked about before. And I don't think I've seen a problem that they've given you guys in this section, or in this chapter, I should say, that is that involved. And I'm not going to show you more than you need to know, because you guys need to know enough already as it is. There's a lot of information in these tests. I'm not going to cover more than you have to know. All right, so let's find each of these probabilities. So again, the part over the whole, we need to know our sample space. They didn't tell us how many master's degrees were conferred total, so we have to do that calculation. We have to find the sum of the frequencies. So we're going to add all of these up. Right, so we're going to say okay, so we have 904 total master's degrees were conferred. Okay, so each of these fractions is going to have a denominator of 904, because that's our total. And the part, or the numerator for each of these fractions, is going to be whatever the frequency is of that particular degree. So business, so 171. Education was 219. And engineering was 91. Okay, so I'm going to add all of those up together. Okay, so you can do that a couple of different ways. We can either just, well, I would say because our final answer needs to be as a decimal, you may as well just plug it in and not kind of do any more work than you have to. So it's 904 plus 91 over 904. Okay, so we take that, we round to 3 decimals. That's how we're getting the 0.532. Now, I do want to show you one other way of doing this problem that is a little bit shorter, potentially, depending on how comfortable you are with reasoning through it. So you'll notice here that there were 5 different options for a major, right? And they're asking for the probability of these 3. So we had to find the probability of all 3 of them. But what we could also have done is we could have done 1 minus the complement of what they asked us for, and then we would have gotten the same answer, right? So we could have done, another way we could have done this is to do 1 minus the complement. Okay, well, what is the complement? The complement of this or this or this is going to be this or this. It's going to be mathematics or English, right? So that's going to be 1 minus the probability of a math degree plus the probability of an English degree. So what was the probability of a math degree? It was 216 out of 904. What was the probability of an English degree? It was 207 out of 904. So if I go to plug that into the calculator, I have 216 out of 904 plus 207 out of 904, and I get that number, right? I get this number. I'm not going to write it down, but it's some number. I want to do 1 minus that number. So I'm going to do 1 minus, and then we talked about this before. If I want to use the answer, I'm going to do second and then answer. So second answer. So 1 minus that, and I'm still getting that 0.532. So it's up to you which of these options feels easier. Later on in this class, you do some other sort of more complicated things where you're going to be doing this type of thing more often because it really is faster than doing it by adding up how many ever things you had. Like here, there were only 5 things to choose from. So adding up 3, not too bad compared to adding up 2 and then subtracting from 1. But if I had 100 things to choose from, and I'm saying I want to choose 98 of them, yeah, I'm not adding up all 98. I'm going to add up the 2 that are the complement and then subtract from 1. Right? So it just depends on how many you have there and kind of what you think is going to be the easiest. So, all right. Okay, of the cartons produced by a company, 5% have a puncture, 8% have a smashed corner, and 0.6% have both a puncture and a smashed corner. Find the probability that a randomly selected carton has a puncture or a smashed corner. Okay, so again, we've got this or, right? The or. That tells us we're using the addition rule, okay? So the addition rule says if I want the probability of puncture, or I'm going to say smashed corner, I'm just going to say punctured or smashed, that's the probability that it's punctured. I'm just going to shorten these. I'm going to run out of room. Plus the probability that it's smashed minus the probability that it's both punctured and smashed, right? Punctured and smashed, right? Because that's the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Right? That's what we're doing here. Okay. So I see that they want our answer to be in percentage form, not decimal form. So I'm not going to convert these percentages to decimals. I'm going to leave them as percentages. Okay, the probability that it's punctured. Well, they said that that was 5%. 5% have a puncture. Okay, so that's 5%. Okay, how many or what percent have a smashed corner? What's the probability that they have a smashed corner? That's 8%. Okay, and then they said 0.6 have both. So minus 0.6% are both. So that's what we're going to plug in. All right, we're going to do 5% plus 8% minus 0.6%. And that's how we're getting 12.4%. Now, if you didn't notice that they want your answer in percentage form, and you were just kind of on a roll and you were like, oh, I'm going to convert to a decimal, then your numbers would have looked like this. Nope, nope, nope. I almost made the mistake I was going to point out to you not to make. So wanted to make sure that you guys are comfortable going back and forth between percentage and decimal. So to go from percent to decimal, you move the decimal to the left 2 places, right? That's how it ends up here. To the left 2 places, that's how it ends up here. To the left 2 places, that's how it ends up here. Or you can just take the number and divide by 100, right? 5 divided by 100, 8 divided by 100, 0.6 divided by 100, right? So then if you would have added these three together, 0.05 plus 0.08 plus 0.006, I plugged something in wrong, hold on. Because you're going to get the same number either way. So let me just see, what did I plug in wrong? Oh, I know what I did. And I did it, oh, you can't see that. I accidentally added when I should have subtracted. So that's why I wasn't getting the same thing. So I'm going to show you how to do something kind of cool in the calculator. What I want to do is I want to redo this math, but I want to change that plus to a minus. So what I'm going to do is I'm going to arrow up, and I don't know if you can see, but it's just highlighted this thing right here. So if I arrow up again, now it's highlighted this. So what I'm going to do is I'm going to hit enter, and it's going to retype that so that I don't have to manually go in and retype it. And then I'm going to arrow over to the left. I'm going to change that addition to a subtraction. And then I'm going to hit enter, and then I get the same. So if I do it this way, I have 12.4%. If I do it this way, I have 0.124 because that's the decimal form of that percent. So if you didn't notice that they want it in percentage form and you did the decimal, you would just then take this and multiply it by 100 or just move to the right 2 places to get the decimal form. Again, you don't want to get something wrong because you didn't put it in the form that they wanted you to put in. If you go and you do all that work to memorize this rule and you plug in the numbers correctly and then you forget to change to the format that they want, we don't want that. Okay. All right, and then also this is just another good illustration of like this idea of like why we're subtracting this, like the probability of A, the probability of B. So probability of A plus probability of B minus probability of A and B. So real quick, I'm just going to use my highlighters here. So if we take the probability of A, so this whole thing, right, including this part here, right, and then we also want the probability of B. So that's this whole thing. You'll notice that we have counted this middle section twice, right? If I do yellow and blue, it makes green, right? I counted it twice. So to get rid of the fact that I counted it twice, I have to subtract one instance of it, right? That's why that rule exists. Okay, moving on. Okay, so more fun with cards. So again, they're not giving you this diagram. I just took a picture of this from the book and put it on this problem so that we could kind of better see what was happening here. All right. Actually, you know what? Before we dive into this, take another water break, have a drink, stand up, stretch, get the blood flowing again. Maybe do some squats or something. Okay. A card is selected at random from a standard deck of 52 playing cards. Find the probability of each event. Okay, randomly selecting a heart or an ace. So remember the addition rule. If I write it enough times, you'll have it memorized, right? Probability of A plus the probability of B minus the probability of both A and B, or the overlap of A and B, right? Okay, so let's start with A. Randomly selecting a heart or an ace. So we're going to do the probability of a heart plus the probability of an ace minus the probability that it's an ace of hearts. Right? Does that make sense? Heart or an ace, so each one individually, and then where they overlap. Where they overlap is ace of hearts. Okay, so let's find the probabilities of each of these things individually. So they're each going to have fractions. And we're not doing something like pulling a heart and then pulling an ace and then pulling a heart of ace. We're not doing that. We're just looking at each of these three things separately. So the denominator for each of these is going to be 52. Okay, the probability of a heart. So hearts make up a quarter of the deck. So something that you might want to keep in mind is there are 13 cards of each uh, oh my gosh, what's the word I'm looking for? Type of each suit. Suit is the word I was looking for. There are 13 cards of every suit. Now, if you don't know that, that's fine. You can just say, well, what is 52 divided by 4? That's 13. So there are 13 hearts. So the probability of a heart is 13 out of 52. Okay, the probability of an ace, well, how many aces are there in the deck? There's one of each suit. There's a total of 4 aces. And then how many ace of hearts are there? Well, there's just the one. There's only one ace of hearts. So when you plug that into the calculator, so again, just be extra safe, use your parentheses, just because we don't really have time to kind of go through all the rules about order of operations and using your calculator and all that. So I'm going to say just play it safe, use parentheses when you're dealing with fractions. All right, so we get that number. If we round to, they said 3 decimal places, that's how we're going to get the 0.308. Okay, that goes to 0.308. Okay, so that was part A. So now let's take a look at part B. So part B says randomly selecting a black suit or a 7. Okay, so that's going to be probability of selecting a black suit plus the probability of selecting a 7 minus their overlap, the probability of selecting a black 7. All right, so again, we're going to create 3 fractions here. There are 52 cards in a deck, so all of these have 52 as their denominator. And we're going to go through and we're going to say how many of each of these things are there to choose from. So how many black cards are there? Well, there are 2 suits that are black cards because half the deck is black. So we can either say, oh, half the deck, so 52 divided by 2, that's 26. Or we could say, oh, 13 of this suit and 13 of this suit is 26, whichever one makes more sense to you. So 26 cards are black. Okay, now we want the probability of a 7. How many 7s are in the deck? Well, there's one of each suit, so there's 4 7s in the deck, right? One in every column. And then we want the probability of a black 7. So how many black 7s are in the deck? Well, I've got a spade and a club. Those are both black and 7. So there are 2 black 7s. So again, we plug this into the calculator. And we get that decimal, which if we round to 3 places is going to give us 0.538. Okay. And then finally we have part C. They want randomly selecting a 5 or a face card. So the probability of a 5 plus the probability of a face card minus the probability that a card is both a 5 and a face card. Well, right off the bat, we're going to say, well, this is 0 because the face cards, remember we talked about the face cards are the kings, queens, and jacks. Those are the only face cards. None of those are fives. There is no overlap between fives and face cards. Now, if we wanted to, we could put a 0 there, and I'm going to when I do this math. I'm just going to say 0 out of 52 because 52 is the denominator for all of these, right? You don't have to actually do this calculation. I'm just showing you that if we were to follow the formula, we're getting the same thing as if we didn't use that. Because in this case, there is no overlap. For these, there absolutely was overlap. We absolutely needed that final, third fraction. But in this one, the third fraction is 0 because there is no overlap. All right, so the probability of a 5. So how many 5s are there in the deck? There are 4 of them, because there's one of each suit. How many face cards are in the deck? Well, there's 3 of each suit, so that's 3, 6, 9, 12. So there are 12 face cards in the deck. Okay. So we're going to say 4 out of 52 plus 12 out of 52. And if you wanted to, you could then subtract 0 out of 52, but you'd get the same thing if you didn't subtract 0. And if we take that and round to 3 decimals, that's how we're getting 0.308. Okay. All right. Okay, decide if the situation involves permutations, combinations, or neither, and then explain your reasoning. All right, so you guys need to make sure that you understand the difference between these two things. A permutation, the order matters. Combination, the order doesn't matter, right? Now, that might be a little confusing because, so I don't know about y'all's high school experience, but for me, I had a locker and I had to put a lock on it, and it was called a combination lock. And that thing absolutely was not a combination lock. It was a permutation lock, because the order that I put the numbers in absolutely mattered. So that's always driven me crazy. The fact that those things are called combination locks, they are not labeled correctly. They are not combination locks. They are permutation locks. So yeah, hopefully that doesn't make it harder for you to remember. But yeah, those things are not called, they're not actually combination locks. They're permutation locks. Because a permutation, the order matters. A password, that's going to be a permutation because the order you type those letters and numbers and symbols and all that in absolutely matters. So a password is a permutation. All right, so let's look at the particular thing that they're asking us to do. The number of ways 11 people can line up in a row for concert tickets. So generally, when you're standing in line, the order that you're in line matters, right? If you're first in line or last in line, who's going to wait the longest? What if they run out of tickets? The first people are going to get it, the last people aren't. The order matters. So if I'm standing in line, the order matters. And if the order matters, it's a permutation. Okay. Right. Okay, determine whether the following problem involves a permutation or a combination and explain your answer. So we just talked about how to determine these things. How many different 7-letter passwords? And before I read any more, I already know it's a permutation because it's a password, right? If it's a password, the order matters, which makes it a permutation. But let's keep reading. How many different 7-letter passwords can be formed from the letters Q, R, S, T, U, V, and W if no repetition of letters is allowed? Now, they're not asking us to actually calculate the number of different letters or anything like that, or I'm sorry, the number of different passwords. They're just wanting to know, given this criteria, is this a permutation or a combination? It's a permutation because the order in which the letters are selected does matter. Okay. So hopefully those will be like easy gimme questions on the test, and you'll get those right. Okay, you have 9 different video games. How many different ways can you arrange the games side by side on a shelf? Okay, so we're going to talk about how to do this, by hand and in the calculator. So for the next few types of problems, there are formulas that you guys are taught, and you have to show that you can use the formula, that you can do the formula by hand. But when it comes to the test, they just want you to know how to plug it into the calculator. They want you to know how to solve the problem using the tools that you have at your disposal, and that means using the calculator. They want you to know that a formula exists, right? It's important to know the calculator's not magic. It's using a formula, and hey, here's the formula it's using, and you can use that formula to do it by hand, but they just want you to do it in the calculator, okay? All right, so here's a few different ways to solve this. So we've got 9 different video games. How many ways can we arrange them side by side on the shelf? Well, I've got 9 different slots on the shelf, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And if I fill each of these blanks in, similar to that very first problem we did, with how many options I have for filling them in, and then I multiply them together, that's going to tell me how many different ways I can arrange them, okay? So for the first slot, I have all 9 to choose from. I can put any of the 9 video games there. But once I put that first video game in, the second slot, there's only 8 video games left to choose from because I've already put one in. And once I put a second one in, now I only have 7 to choose from. And once I've put that in, now I only have 6 to choose from. And now I only have 5 and 4 and 3 and 2. And when I get to my last one, there's just one left to choose from. Okay. So you could plug this into your calculator. 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And you would get this number. But another way to write this is called factorial, right? This is 9 factorial. And what that factorial means, that exclamation mark, it means take that number and multiply it by all of the integers below it all the way down to 1, right? So I didn't have to write all of this out. I could have just written 9 exclamation mark, 9 factorial, and then plugged it into the calculator. Okay, so let's talk about how to plug that into the calculator. So you're going to do 9. Okay, so I'm going to type in a 9, and then I'm going to go, oh, you guys can't see that. I'm going to, let me write this over here. The calculator has to be over here, otherwise you get the glare. So then what I'm going to do is I'm going to hit this math button right here. I'm going to go math, right? So we hit math. So you type a 9 and then you hit math, and then you're going to arrow over to probability. So I'm going to use the arrow to get all the way over here. I'm going to arrow over to probability. Okay. And now I'm looking at the probability menu and I can see that the 4th option right here is the exclamation mark. So I'm going to select 4, which is the exclamation mark. So I can either arrow down to 4 and then hit enter, or if I'm just here, right, like I go over to probability, I can just hit the number 4, right? I can literally just hit the number 4 and it will select the 4th option there. Okay, so now what I have in the calculator is 9 factorial, and if I hit enter, look at that, we get the exact same number, because rather than having to do it by hand, we had the calculator do it for us. So you can see how long it took me to type that in versus if I know where the menu is, how long it takes me to put that in. Okay, so you want to make sure that you know how to access the factorial. It's math, probability, number 4. Okay, all right. Okay, there are 43 runners in a race. How many ways can the runners finish first, second, and third? Okay, So first thing we need to determine is this a permutation or a combination? So this is a permutation because the order matters, right? I care if I'm first, second, or third, right? So what we're going to do, and I'm going to use this notation here, is the NPR as opposed to NCR. So this is the notation for combination. This is for permutation. And yeah, so for permutation, often the way that they read this is N things taken R at a time. And since it's a permutation, it's where order matters. Right, that's this. Okay. So what do we mean when we say N things taken R at a time? How many things are there? How many runners are there? There are 43 runners. That's our N. N is 43. It's like our sample space, right? N is your sample size. There's 43 runners total. Okay, and what are we looking for? We're looking for how many ways the runners can finish first and second and third. First, second, third, that's 3 different places that we're trying to fill in. So that's a 3. Okay. So we're going to solve this problem multiple ways. We're going to start by doing it the easiest way. Okay. We're going to do it in the calculator. So to do this in the calculator, you can either start by typing in your 43. Actually, if you have like one level older than this of this calculator, you actually do have to start with the 43. But if you have this, this is a really expensive calculator. I just got it because it's pretty and because I do this for a living. But if you guys are just taking this class and that's the only time you're going to need the calculator, you don't need to have bought such a fancy calculator. So you might have an older version, or maybe you're using an emulator on your phone or something that is emulating a slightly older version. So like this, I don't know if you can see with the reflection there. This is an 84 plus CE. You might have a TI-83. If you have a TI-83, you have to start by typing in your 43. Then what we're going to do is we're going to, again, go to math. Okay. So we do the math button. We're going to again arrow over to probability, right? Arrow over to probability. And you can see here, options 2 and 3 is the NPR and the NCR. So I'm going to arrow down to NPR, or I'm just going to select number 2, right? 2, which is NPR. And you're going to hit enter. Okay. Sorry, let's enter. Trying to type in all the steps here. I don't think I said enter last time. Well, you know what? I don't need to say enter because if you just select number 2, like if you just hit the number 2, it'll still do it and you won't have to hit enter. So I'm not going to say that here. I didn't say it last time, so I'm not going to say it here. Okay, so NPR, and then we have to tell it what the R value is. So the R value in this case was 3. Oh, sorry, I didn't start with. So we start with 43. We start with 43. Then we hit math. Then we arrow over to probability. Then we select the second option, which is NPR. Then we give it number 3. And you can see on my calculator, the fancy one, it creates this little 43 P, and then I can put my 3 in, and then I can hit enter. And I get my answer of 74,046. So if on the fancy calculator, if I don't put the 43 in first, it's still going to prompt me to fill that in. Like if I go math, probability, NPR, it says, hey, what did you want for your first number? And I can type it in there. But if you have the older version, you have to start with 43, then go NPR, then go 3. Okay, so that's how we do it in the calculator. That's the fastest way to do it, right? Fastest way, calculator. All right, but there's another way to do it. We can do kind of the way that we've done several of these problems where we say, okay, I'm going to make a blank for each of these three places, right? This is first place, this is second place, and this is third place. So how many runners are there? There's 43. So that means that for first place, there are 43 options. But once somebody places first, once they finish the race, there's no longer 43 people to choose from for who gets second place. Now there's only 42 people to choose from. And once somebody finishes second, now there's only 41 people to choose from for who finishes third. So if we take those, 43 times 42 times 41, we're still getting that same number, 74,046, right? Still getting the same thing. And then there is yet again another way to solve this. So I was talking before about the formulas, right? So the formula for a permutation is n factorial over n minus r factorial. N is how many things you have total. R is the number of ones that you are selecting. So n is 43. There's 43 runners total. Again, n is 43. R is 3. We're selecting 3 of them. And then we're doing factorial. So I'm going to clean this up a little bit. Right? 43 minus 3 is 40. And I mean, if you were taking this class in person, they might go through and kind of show you how this would like reduce out and you would get this. Right? So they might show you like, oh, well, this is 43 times 42 times 41 times 40 times 30, times 39 times 38, so on and so forth, right? And then here, 40 factorial, well, that's 40 times 39 times 38 times 37, all the way down to 1. So this whole chunk here of 40 factorial over 40 factorial, these are going to cancel. And all you're really left with is, hey, look at that. 43 times 42 times 41. So it's good to know that this formula exists, but you do not have to do this by hand. They don't want you to do this by hand. They want you to do this. I mean, maybe in the homeworks, they want you to, hey, take a minute, get yourself familiar with this. And then when you go to take the test, just do this, right? They're not expecting you to take all the time to do this. So if we were to plug this into the calculator this way, we would have 43, again, to get factorial, do that, divided by 40 factorial. So however you do it, you're getting the same answer, but when it comes to the test, don't do it the long way. This would even be the long way. This would be the shortest way. Okay? You want to save yourself as much time as possible. All right, we're getting close to the end. All right, there are 12 finalists in a singing competition. The top 6 singers receive prizes. How many ways can the singers finish? 1st through 6th. So again, this is just going to be, is this a permutation or a combination? Since the order matters, it's a permutation. So we're going to use NPR. So there are 12 singers to choose from, and we're going to rank the top 6. So in the calculator, we're going to go 12, math, arrow over to probability. Oh, also, let me go back. So at first I was arrowing to the right to get to probability, right? Like I would go to the right 1, 2, 3. But if I arrow to the left, it's like it goes to the left and around. So if I arrow to the left, it starts back over on this side and it only takes me 2 clicks to get over to probability. So just be aware that you can arrow your menus that way as well. And then I want NPR because this is a permutation because order matters, and we're choosing 6. And that's how we get that there's 665,280 different ways that the singers can finish 1st through 6th. Okay. All right. In order to conduct an experiment, 4 subjects are randomly selected from a group of 42 subjects. How many different groups of 4 subjects are possible? Okay, so for this one, the order doesn't matter, right? I'm in a group with other subjects. I don't care which one of us was chosen first. The order doesn't matter. Or we're not being like placed like the first one in group or the second or third or fourth. So since the order doesn't matter, this is NCR. It's a combination. So there's 42 subjects and we are choosing 4 subjects randomly. So we're saying how many different ways can we do that, or how many different groups of 4 subjects are possible, right? So again, we're going to go 42. We're going to go math. We're going to arrow over to probability. And we're going to go down to NCR, because this is a combination because the order doesn't matter. And we're going to put in a 4. And that's how we get 111,930. Okay, a class has 27 students. How many different ways can 6 students form a group for an activity? And assume that the order of the students is not important. Okay, order is not important, then it's a combination. We've got 27 students to choose from, and we're going to be pulling 6 of them in groups of 6 for the activity. So we go 27, we go math, arrow over to probability, down to NCR, because it's a combination because order doesn't matter. And then we say we're choosing 6 of them. And that's how we're getting that number. All right. A certain lottery has 25 numbers. In how many different ways can 4 of the numbers be selected? And assume that the order of selection is not important. So order is not important. So this is a combination. There's 25 numbers to choose from. We're choosing 4 of them. So 25, we go math. We arrow over to probability. We choose NCR because it's a combination, because the order doesn't matter. We're choosing 4 of them. And that's how we get 12,650. Okay. And yeah, so now we are back at the beginning. Okay, so I want to give you guys the ASC's homepage is library.datonastate.edu/ASC. It used to be just datonastate.edu/ASC, but now you have to type in the library because the library is we're all part of the same department, the library, the writing center, and the academic support center. So the library like hosts our website. But anyway, the important thing here is that if you go to this website, you can see the hours for every academic support center. We have one on every campus except for the ATC. So if you want to go in and get help in person, you can check the hours for the location that's closest to you. Don't forget that the ASC that's in building 115 at the Daytona campus, so DB 115, so that's the one that's located inside the library. So on the Daytona campus, we have 2 ASCs. We have one in building 500 and then we have one in building 115. So the one in building 115 is open on Saturdays from 8 to 4. And the people that are there on Saturdays can help with statistics. So don't forget that you can go in for help on Saturdays. And then that location, Monday through Thursday, is 8 to 8. So 8 a.m. to 8 p.m. And then on Friday, it's 8 to 5. Okay. So there is in-person help after hours. Now, I know if you're taking an online class, it's probably because maybe you're working a 9 to 5, or you can't, like maybe you live kind of farther away and you can't physically come in. So we have the virtual chat, which is Monday through Thursday from 8 to 7:30 p.m. So even if you do work 9 to 5, you can get help after 5. And then on Fridays, it's from 8 to 5. And some people mistakenly think that the virtual chat is like a chat bot and it's just like AI. No, it's connecting you with an actual human being. It's connecting you with one of the learning specialists who work at the Academic Support Center. We all have certain hours a week that we are manning the chat. So I'm on chat for several hours a week. There are other learning specialists besides me that can help with statistics. Um, Many of them can help with statistics, as well as many of our student workers, our peer tutors. So if it's not a time that, that I'm on chat, that doesn't mean you can't get help with stats. It just means that you'll be talking to somebody else. Also, for the online chat, um, if you have a question that you just want to like type in, what your question is, and they just type the answer, that's fine. You can do that. I am a very visual learner and teacher. And so often if I'm helping somebody on chat, I'm going to switch to a video call. So we have the ability to do that with the virtual chat. So it looks just like this. We use Teams so you guys can, see me working out the problem. There's also a way where you can do a screen share. You don't have to be tech savvy. We walk you through it, where you can share your screen if you're like, I don't even know how to describe to you this chart I'm looking at, or I can't explain what I'm looking at. You can just show us your screen and we can do it from there. Um, the other thing that I want to talk about is that your instructor is a great resource. If you think that you've incorrectly been marked wrong on a problem in your Pearson work, reach out to your instructor. They can clarify what went wrong, or there might be a legitimate glitch or bug or error or something like that. And you won't know unless you ask. So don't hesitate to reach out to your instructor for things like that, as well as just help, understanding the concepts. They're there for you. They want to help. They want you to succeed. So reach out to your instructor. Your instructor might have office hours where they are in person on campus, so take a look at that. And then of course, if you want to, um, work with me specifically, I'm at different campuses on different days. Many of the learning specialists are. So on Mondays, and this will all be in the email, but on Mondays, I'm in New Smyrna from what time? 8 to 5. And then Tuesdays, I'm in Flagler Palm Coast, also 8 to 5. And then Wednesdays, I'm in Daytona at the 115 ASC up until 12:15. That's my short day. And then Thursday, I'm again in 115 until 5:15. And then Friday, I'm again in Daytona until 5 p.m. So if you want to go in person to see me specifically, that's when I'm available. But don't feel like you have to come see me specifically. Almost any of the learning specialists can help with this class. And like I said, many of the peer tutors as well. Finn, if you wanted to, I don't remember if you already gave me your email address, but if you wanted to send me your email address, I will send you a recording of the session today. I'll put you on the list. You can either put your email in the chat, or you can just email it to me. I've put my email in the chat. I have 2 email addresses because I go by my middle name. I know it's confusing, sorry. But you can send it either to maxine.horn or brandy.horn@Daytona State. So yeah, so I always suggest to use your school email just for a variety of things. I have run into issues before where like emails don't go through because like, I don't know, it marks it as like spam or something. But if it's a Daytona State email, it'll never have a problem with it. So yeah, so I'll give you a second to get that typed in there. But while you're doing that, yeah, just kind of overall, don't hesitate to reach out to, whatever you can reach out to to get help. And don't hesitate to use your calculator. Yeah, definitely. The farther you go in this class, the more important having that calculator or that emulator for that calculator is going to be. I was told the other day that one of the instructors actually has a particular emulator that they suggest that people get. So if your instructor has suggested one in particular, then definitely go for that. It's definitely cheaper to buy an app on the phone than it is to buy a $100 calculator. So unless you're going to be going even farther in math and taking advanced stats or other advanced courses, you don't need to spend $100 on your calculator. So I'll give you a minute to finish typing that. Okay. All right. Well, that does it for today. I hope this has been helpful. Oh, nope, you are still typing. Sorry, I don't want to cut you off. All right. All right, absolutely. Thanks so much and good luck, everyone.